This is part 3 of a series on important statistical distributions. Here we study the normal distribution. The instructional design for this program was developed by David Kleinbaum, statistician, and Anna Washington, educator. The narration was done by David Kleinbaum. The normal distribution is of central importance in statistics. As this picture shows, the normal distribution has a bell-shaped curve. When we look at a whole array of variables defined from naturally occurring phenomena, for example, number of arrivals, amount of rainfall, number of deaths, blood pressure, baby weight, body temperature, and other naturally occurring variables, even down to size of trees, we generally find the normal distribution to be widely, though not universally, applicable. That's a big reason for studying the normal distribution. It's so widely applicable. There is also a second good reason for the importance of the normal distribution in statistics. This second reason involves the central limit theorem. This theorem, coming from mathematical theory, says that through sampling we can end up considering the normal distribution even when we start out observing some other distribution, no matter how non-normal. To see how the central limit theorem performs this miracle, imagine what would happen if we drew a sample and conducted an opinion poll about a controversial political issue which most people either strongly favored or opposed. Suppose for each person we checked on a 1 to 20 scale how much he or she favored or opposed the issue. Since most people would feel strongly one way or the other, the resulting distribution of scores would tend to reflect this polarization. More scores would fall at each end of the distribution and it would be bimodal, certainly not a normal distribution. Now consider what would happen if instead of taking one sample, we looked at several samples from the same community. Since each sample comes from the same population, we can still expect the distributions to be bimodal and look pretty much the same, although not exactly the same. But suppose for each of these samples we focused only on the sample mean x bar, which we might wish to use as a summary measure of the scores for a given sample. We would then be considering a new random variable, x bar, which, like any random variable, will vary from sample to sample. If we collect all these x bars and plot their distribution, what do you think will result? The answer is that a histogram of x bars will approximately have the bell-shaped curve. That is to say, the new distribution formed from x bar will have the normal distribution. So the central limit theorem states that no matter what the distribution of x, the distribution of x bar will always follow the normal distribution, provided the sample size used in computing x bar for a single sample is moderately large, larger than say 20. Now you can see the wide applicability of the normal distribution. This section, section number 3, and the next 2 will all deal with the normal distribution. Sections 1 and 2 already completed dealt with computing binomial and Poisson probabilities. This section will show you how to compute probabilities for the normal distribution. Later sections, numbers 4 and 5, will use the normal distribution to solve other problems, computing normal percentiles and approximating binomial probabilities. The recommended approach for computing probabilities involving the normal distribution is similar to that for binomial and Poisson distributions. Given a problem, first check the properties to see if the normal distribution applies, then determine the key parameters, and finally look up your answer in a table of the normal distribution. For the last 2 steps, it will help considerably to draw the picture of the distribution and the probability in question. You may remember that for the binomial and Poisson distributions, you did not need to draw the picture, but for normally distributed variables, the final step is a bit more complicated, and a picture helps considerably in determining how to use the table to find your answer. The first important property of the normal distribution is that it describes a continuous random variable. The graph of the distribution thus gives a smooth curve. This property distinguishes the normal from the binomial and Poisson distributions, which are discrete. The second important property of the normal distribution is that it is symmetric. That is, one half is a mirror image of the other half. This property distinguishes the normal distribution from other continuous distributions which are not symmetric. This symmetry property can often be used to determine probabilities of interest from tables of the normal distribution. For example, this student is seeking the area in the right tail of the curve which he has drawn. To get his answer, however, he must recognize that the area he seeks has an equivalent mirror image area in the left tail which can be found in a table. The third important property, which we have already seen, is that the normal distribution is bell-shaped. This means that most of the area in the normal curve is in the middle, and that the area in each tail gets smaller at the same rate as you go further out in the tail. This property distinguishes the normal from other symmetric distributions arising from natural phenomena. As far as notation is concerned, N denotes the normal distribution in the same way that BIN denotes binomial and POI denotes Poisson. The parameters must also be written in brackets in a similar way. The two parameters of the normal distribution are the mean mu and the standard deviation sigma. As with the binomial and Poisson distributions, the parameters are necessary to look up probabilities in the table. The shape and location of the distribution are dependent on these two parameters, mu and sigma. Because of symmetry, the mean mu is at the exact center of the distribution. Notice that as the mean increases from 10 to 20 to 30, the center of the distribution is shifted to the right. Therefore, changing mu changes the location of the distribution. The standard deviation sigma is given by the distance from the mean to the inflection point on the curve. The inflection point is the place on the curve where the curve changes from convex to concave. Observe what happens as the standard deviation changes. As the standard deviation gets larger, the curve gets more spread out. That is, there is more variability between possible observations. Here, as sigma goes from 10 to 20 to 30, the curve gets more spread out. Therefore, changing sigma changes the shape of the distribution. For the normal distribution, the kinds of probabilities we are seeking are areas under the curve as in the graph and formula at the top, not single points as in the graph and formula at the bottom. The value of a single point like that at the bottom picture of the normal distribution always gives a probability of 0. This is another typical probability question for the normal distribution. To find the probability that x is between two values like 60 and 70, we express the probability that x is between two numbers as an inequality, x greater than 60 and x less than 70. We can equivalently express this probability using the second formula below, which includes the endpoints 60 and 70. The two formulae are equivalent because the probability of x at single points like 60 or 70 is always 0. Now let's go on to a realistic probability question. Take, for example, the case of a community for which the birth weights of male babies is known to have a mean of 3,500 grams and the standard deviation of 500 grams. A clinician or other investigator may wish to know whether a boy born weighing 4,600 grams is a remarkably heavy baby. That is, she may ask, what proportion of male births in the community weighs 4,600 grams or more? Incidentally, by proportion, we mean the same thing as probability. The population proportion, that is, the number born weighing 4,600 or more, divided by the total number born in the community, equivalently expresses the probability of being born weighing 4,600 or more. Now, for the random variable birth weight, the first question we ask is whether the variable is normally distributed. Is the variable continuous, symmetric, and bell-shaped? Baby weight is certainly continuous. However, at this point in the course, we will not really be able to evaluate normality adequately, although we could certainly graph the data to determine if the distribution is approximately bell-shaped. For purposes of learning to compute probabilities, we will have to, for now, assume normality if the variable is continuous. Later, a more complete approach for distinguishing normal variables from others will be presented. Having checked the properties and decided the distribution to be normal, we write at the top the parameters in the proper notation with mu equal to 3,500 and sigma equal to 500. And we draw the picture to identify the probability in question, the probability that X, birth weight, is equal to or greater than 4,600. This is the area above 4,600, that is, in the right tail of the distribution. We are ready to consult a table of normal probabilities. Now, if you try to find a table of probabilities for the normal distribution with parameters mu 3,500 and sigma 500, you will be wasting your time. There is only one normal table available for you to use, and it considers only one set of parameters. That one and only table is called the standard normal or z-table. It gives probabilities for what is customarily called the standard normal or z distribution, which has mu of 0 and sigma of 1. But you will see that the probability we are seeking can still be computed using this table. Actually, having only one table for the normal distribution is much less complicated than having many, when you consider the infinite values of mu and sigma, and therefore the infinite number of tables you might have to juggle. Because we only have one table to work with, our problem about baby weight, which we called X, must now be transformed. We have now to figure out how to convert the probability question about X to an equivalent probability question about Z, so we can use the z-table to look it up. But before converting X to Z, put the baby problem on hold and take a look at the z-table itself and how to use it. Different textbooks often use slightly different formats for presenting the normal 0-1 or Z distribution. This z-table, which is provided in your course notes, gives the probabilities of areas only for the left tail of the z distribution, going from very small areas like for z equal to -2 up to large areas like for z equal to 2. For example, to find the probability that z is equal to or less than 2.2, that is the area under the standard normal curve to the left of 2.2 as drawn in the picture, enter the table at 2.2 in the z column and read the probability 0.9861 in the probability column. To find the probability that z is less than or equal to -0.5, draw the picture first. This area is smaller than the one just seen and considers a negative value of z, but it is still the same kind of area, a left tail area, that is less than. Looking up -0.5 on the z-table gives a probability of 0.3085. The usual z-table gives only probabilities for areas less than a value of z. that is, left-tailed areas. But because of symmetry, the same table can be used to find probabilities with tails to the right, or values of z greater than. In this example, the probability that z is greater than 0.5 is exactly equal to the probability that z is less than minus 0.5. Now back to weighing babies. How can we get from a probability question about normal x to an equivalent question about standard normal z, which can be looked up in the z-table? We need a conversion formula, a way to change x to z, also called zifying. We will now show you how to zify or convert x to z. To follow the logic of the formula, imagine x and z on graph paper. The normal x and the standard normal z are graphed on the same axis. The z in black with a mean of 0 is located at 0, the left curve, and the x in red with mean of 3500 at 3500, the right curve. The z-curve is tall and skinny because of the standard deviation of 1, and the x-curve is short and spread out because of the standard deviation of 500. We can convert x to z or zify by first shifting the x-curve 3500 units to the left, starting like this, and continuing like this, and then squeezing it together to make it tall and skinny to get the z-curve, like this, and finally like this. The shaded area we seek will likewise be shifted and compressed, but the amount of area will remain the same, since the total area under both x and z curves is always 1. Now, if you didn't get it, don't be too concerned, just learn the formula. This is the precise zifying formula. X changes to z by subtracting mu and dividing by sigma. That is, x equals x minus mu over sigma. Now, how do we use this formula in our baby weight problem? The problem in symbolic notation is at the top. It reads, we have a normally distributed variable x with mean 3500 and standard deviation 500, and we wish to find the probability that x is greater than 4600. To find it, we zify, and the result is given at the bottom. It reads, for a normally distributed variable z with mean 0 and standard deviation 1, we must find the probability that z is greater than 4600 minus 3500 divided by 500. And here's the result in areas and formulas before and after converting x to z. After doing the arithmetic of 4600 minus 3500 divided by 500, we get at the bottom right 2.2. This is the figure to look up in the z-table. Remembering that the usual z-table only gives areas with a left tail and we have a right tail problem, we must use symmetry to look up minus 2.2 instead of 2.2. In the table under z equals to minus 2.2, we read the answer, 0.0139. That is, the probability that a male birth weight will exceed 4,600 grams in this community is 0.0139. In terms of percents, we can express this result by multiplying by 100, or moving the decimal over 2 places to obtain 1.39%. We have obtained the statistical answer. A birth weight of 4,600 or more in this community has a probability of 0.0931. That is, it occurs 1.39% of the time. But what is the clinical answer or interpretation of this data? Is this birth weight rare? Is it a remarkably heavy baby or not? Actually, to evaluate how rare is rare, the statistician should not supply the clinical adjectives, but rather must leave interpretation up to an investigator who is clinically familiar with the variables in question. Let's compute one more normal probability. This time we will be looking at the workers in a certain chemical industry. Suppose it can be assumed that the entire population of workers has hemoglobin levels which follow a normal distribution with mean 14.8 and standard deviation 1.2. An occupational health physician for this industry might want to know the proportion of these workers with clinically normal hemoglobin levels using an accepted standard for normal ranges between 13, below which a person may be considered anemic, and 16, above which a person may be considered to be of risk for coronary disease. This time we will let Y stand for the variable hemoglobin level, and we rewrite the problem as a probability statement and draw the picture. For the normal random variable Y, with parameters of mean 14.8 and standard deviation 1.2, we seek the probability that Y is between 13 and 16. To find the probability, first zify the probability question about Y into an equivalent question about Z. Here Y is zified the same as we previously did for X by subtracting mu and dividing by sigma, although this time we must zify two numbers instead of just one. Observe the legal code for inequalities. That is, with an inequality like this, it is legal to add, subtract, or perform any mathematical operation on it as long as you do it to every member of the inequality. If you want to zify, do it to every part of the expression. That's what we've done here. 13 on the left is zified. Y in the middle is changed to Z. And 16 on the top right is zified. The resulting formula after zifying is reduced arithmetically to obtain the pair of numbers Z is between minus 1.5 and 1. We want to look up these two numbers in the Z table to get the area under the curve between minus 1.5 and 1. The area desired, shown in the bottom curve between minus 1.5 and 1, is equal to the large area to the left of 1, minus the small area to the left of minus 1.5. From the Z table, we will find that the probability that Z is less than 1, the top area on your left, is 0.8413. And the probability that Z is less than minus 1.5, the top area on your right, is 0.0668. Subtracting, we get 0.7745, the probability for the area sought. The occupational health physician has thus learned that 77.5% of the workers in this chemical industry have clinically normal hemoglobin levels. The interpretation of this finding must consider comparative percentages for other industries or for the general population. Here is a final problem for you to figure out when the presentation is finished. Suppose the IQ of children of faculty members at a large university has population mean of 120 and standard deviation of 10. Find the probability that the IQ of a randomly selected child will be between 110 and 125. To repeat the procedure for you to use, given a probability problem, check the three properties to see if the distribution is normal. Determine the parameters mu and sigma. Draw the picture, and then convert x to z to find the answer in the table. Part 3 is now complete. We suggest working some problems dealing with normal probabilities before going on to Part 4, computing normal percentiles.